All right, so again, you guys, I'm sorry about the noise. Let's do our best to stay focused. All right, so number 2, Roy builds this giant slingshot, right? And he's going to launch himself up over the building. All right? I always like to read through the whole problem just to get a sense for what's going on. So he's going to get launched. It gives you some information about the top of his path. In part C, like I said, he lands in this garbage truck. Okay? So let's make a quick sketch of the path he's going to follow. So you've got the slingshot, right? He's going to get launched through the air before landing in the garbage truck. Cool? All right, so throughout the course of the problem, what forces are going to act on him? What forces act on him during the course of this entire motion? So Lucas, give me one. Gravity, right? Okay, so forces, we got gravity. That's always acting on him. Do we really need to worry about it? No, because it's a conservative force, right? Conservative, right? So that's not going to change our total energy. Everybody good up to there? All right, you had a hand up. Give me another one. Elastic force, because we're looking for forces, not energies. Okay. All right. So another force is the force of the rubber band pushing him forward. So there's something very important about the force of that rubber band. It's a conservative force, right? And we know that because we account for the work done by the rubber band by measuring elastic potential energy. So there's a form of energy associated with that force. So that force of the rubber band won't change the total energy either. Does that make sense? All right, there's only one other force. What do you got? So from here to here, you got the rubber band and gravity. Here you've got just gravity. Oh, I guess and air resistance, which we always ignore. And the garbage, right? When he hits the truck, the garbage is going to stop him, right? Okay, so which one of those three forces is the non-conservative one? The garbage. So what's the only time the total energy is going to change? When he hits the garbage. So the only time I need to worry about work is here in the garbage truck. Does that make sense? Yeah, Emma. So to give you a really good definition, we got to go into a little bit more depth. Basically what I've been telling you guys is a force is conservative if it's responsible for a form of potential energy. So the reason we call gravity a conservative force is because we have gravitational potential energy. Similarly, when we stretch the rubber band, we get elastic potential energy, right? And so, I mean, here, look. Right now, this has elastic potential energy, right? If I let it go, that elastic potential energy converts to kinetic energy. Sorry, Sally. The kinetic energy, the elastic energy converts to kinetic energy, but the total hasn't changed at all, right? All you've done is convert one form to another. Does that make sense? All right. Everybody good? All right, so with that in mind, let's go through and write down some information. So I'm going to kind of color code. So at this point, here are the things I know. I know his height is 0. I know his velocity is 0. Does that mean the total energy is 0?
No.
No, why not, Lucas? Because there's elastic potential energy here, right? Good? All right. At this point, the problem tells you the slingshot is 10 meters tall, and he leaves it with some velocity. We just don't know what that velocity is. Okay? And the problem also tells us that when he gets to the top of his path, he's 50 meters up, and his velocity is 20 meters a second. So that's all in the, sort of in the text of the problem. So are we good up to there? Milena, how you doing? You good? Everybody good? Tom, you good? Brianna, how about you? You good? Everybody happy? All right, so autopilot. Anywhere you know the height, find the GPE. Anywhere you know the velocity, find the KE. Do I need to write those out, or can I just sort of Like, everybody cool if I do this? If you find the GPE and the KE and find your total, it turns out to be 41,400 joules. Is that okay that I just, everybody okay with how I got that? Yeah. All right. So the question wants to know the velocity here at this red dot. And I think what happened is a lot of people fixated on these 2 points, the green and the red. But the problem is if you fixate on the green and the red points, we have 2 unknowns. We don't know the velocity at the red or the EPE at the green. Okay? But what should be true about the total energy everywhere except for over there in the yellow? It doesn't change. So that means that throughout all of the pink, the total energy is constant, right? So for that whole chunk, there's my total energy. Follow? So now what we can do is, up here at the red, we know our height, so we can find the GPE. We know the total energy, so we can subtract to get the KE and find the velocity. Good? All right. So, do you guys want me to write out all the numbers? Anybody want me to? Okay. So, if you do this, this velocity ends up being like 34.4 meters a second. Good? Yeah.
Okay, so does that mean that the EPE at the beginning is the
Let me hold that for 1 second, but yes, 100%. So is everybody good with how I got part A? All right, now part B says, what's the elastic potential? No, part B says, what's the spring constant of the rubber band, right? Okay, so to find that spring constant, I need to be thinking about the elastic potential energy, right? So, my GPE is 0, my KE is 0. What's my total energy down there at the green dot, you guys? 41,000, right? So what's the EPE at the green dot? 41,000, right? So now I can just do this. I know my EPE is 41,000. I don't know K. Now, X. What are we going to use for X? Yeah.
It's like T.
The cart's not going at all?
Yeah, only stop and then turn to the right.
It's 1, 2, 3, 4, 5, 6.
All right. So, here's the deal, you guys. Here's the last thing. What am I going to use for X? Yeah, you got to use the hypotenuse of this little triangle in here, right? So it turns out to be 18. So yeah, it's like 18 point something. And then solve for your K. Yeah. Why do you use that? Because when I passed out the test, one of the things I told you was that you could assume that at the top up here that the slingshot wasn't stretched at all. Okay, and X represents how far you stretch it. So you're taking it from an unstretched position and then stretching it down at an angle down to the ground. Good? All right, everybody set on that? It turns out to like 250, 255. Oh, and what are the units for spring constant? Did you remember to square your... What are the units for spring constant, you guys? It does have units. Coefficient of friction doesn't. It's newtons per meter. Newtons per meter.
Yeah, you're right.
Cool?
255.
All right. Any problems with this? Tom, you good back there? Sam, how about you? You good? Alex, how about you? Good? Elena? Any problems? Problems? Okay. So finally, now we got to do part C. So for part C, let's zoom in. So here's the garbage truck. The problem tells us that when Roy hits it, he's at a height of 5 meters, but we don't know his velocity, right? But then it tells us that he sinks 3 meters into the garbage before he stops, right? So at the point where he stops, what's the height going to be, you guys? 2. So, find your total energy. It's just going to be GPE. Turns out to be 1170. Is it 76 or 74? 76. Good. All right. How is this part different from everything we've done so far in this problem? There's a non-conservative force, so my total energy changes. And a lot of people got stuck because you don't know the velocity here. Does it matter? No, because what's the total energy when he hits the truck? 41,000, right? So you don't even need to find that velocity. All you got to do is go, oh, well, up until here, the only force has been gravity, so the total energy here is still... That's a J. Abby.
Wait, so you're saying the total energy at the height of 2 is that? Okay,
Yes.
I'm good.
Does that make sense, you guys? So look, his total energy went from 41,000 to 1,000, so he lost a whole bunch of energy. Why? Why did he lose the energy, guys?
Because the non-conservative force.
The garbage pushed him upwards and stopped his downward motion, right? Follow? Everybody good? Okay. So what's my next step, you guys? Use the second equation to find your work.
Oh, wait, sorry.
So my work is TE final minus TE initial, which gives you and now what?
You said equal that.
Plug it into the top equation and find your force, right? What do I use for my displacement? 3, because that's the distance he sinks while the garbage is stopping him. And technically, I guess the 3 is negative, right? Because he's going down 3 meters. Gives you a positive force. Cool, you guys? Was that too fast? Did I lose anybody there?
Okay, wait.
Yeah.
When it says like find average stopping force, like what is the average?
It just means, technically speaking, as he sinks through the garbage, the force might change. You know, like maybe he hits a roll of toilet paper at the beginning, and then he hits like a chair, and that exerts more force. I don't know. If that was what confused you, I apologize. But
That was not all.
what's that?
That was not all that.
I gotcha. Yeah. It just means the force might change. So technically, that equation gives you the average.
Oh, what's the final answer?
13,408. Oh, no, wrong.
Have you explained it? It seems so easy.
That's every single time.
Yeah, that's like the most common answer. It looks so easy when you do it,
Yeah,
right?
every time.
And then you get it home and you're like, what the bleep is this, right? So I get it. So, but what I will say is, every single problem starts out this way, where you identify height and velocity. Identify height and velocity. When you get stuck, what do I know about the total energy? Is it constant or changing? I know. I hear you. Take practice. Good, you guys? All right. So that's number 2. Any problems with it? Milena, are you good?
Yes.
Everybody set? All right. Are there some of you that want me to go over number 1 also? Yes? Okay, so let's do that.